Hello friends, welcome to another tutorial in electromagnetics and antennas series. In this tutorial we'll talk about charge density. We'll talk about types of charge densities and we'll do a couple of numericals along with the reference of appearance of charge density in Maxwell's equation. If this is something that interests you, then please keep watching. Charge density is the density of charge on a line or a surface or a volume, and it is denoted by this symbol rho. The understanding of charge density is not that tough, but the representation of charge density in terms of the line, surface and volume in integral is something that we need to take care of while solving a lot of numericals and while interpreting the real world scenarios. So depending upon that, we have three types of charge densities. The line charge density, which is denoted by rho L, surface charge density denoted by rho S, and volume charge density denoted by rho V. Let's understand rho L. We consider a line or a wire which is most suitable for this understanding because we can place some charge on the wire. So we have a thin wire with total charge Q spread all across the wire, and the length of the wire is L. Now understandably, the density of the charge on this wire can be easily found using this formula, where the line charge density is the total charge upon the total length. So Q upon L will be the line charge density. However, if we take a small length dl and if we take dq to be the charge on that small length, rho L changes to dq by dl. The value of dq turns out to be rho L dl, and if we integrate dq, adding up all the dq's on the line will give me the total charge. This is total charge, and the total charge becomes rho L dl, and this is line integral. So this is very important form of writing the total charge in terms of the charge density, that it is rho L dl, line integral. On the similar lines, if we consider a surface, so we can assume a sheet with charge Q spread all across the sheet, and the area A, total area of this sheet is A, total number of charge is Q. So rho S, so this will be surface charge density. Rho S will be total charge upon total area. However, if we take a small area dA, if we take dQ to be this differential charge, rho S changes to dQ upon dA, and we get dq to be equivalent to rho S dA. Integration of dq will give me the total charge, which is what we are looking for right now. So total charge in terms of charge density becomes rho S ds, surface integral. So very important format, and by this time you'll be comfortable in calculating rho V. Also, we need to consider some volume. In this case, I've considered a cube with some charge inside it, and the area of the this should be the volume V. So we have a cube with volume V and total charge inside is Q, so rho V will become Q upon volume. And if I take up a small differential volume dV along with the small differential charge in that, rho V will become dQ by dV. And and the total charge becomes rho v dv. And this format is widely used in Maxwell's first equation, that the total charge is rho v dv, and of course the total charge is equivalent to the flux, and divergence of flux density gives me the total flux, so it becomes equivalent to rho v. Well, that's a different story, but you'll see rho v to be featured in the Maxwell's first equation. Now, having understood the basic definitions of these charge densities and their representation, I want to take up two questions. The first question says that if the line charge density on a wire placed in z-axis is 12z square microcoulomb per meter, of course the rho L is given, we need to find total charge, and the wire is extending from -2 to +2. So the first step will be to draw the representational diagram of this problem, where I placed a wire going from -2 to 2 in the z-axis, and total charge density on this length of wire is 12z square. Microcoulomb per meter are the units. So rho L is 12 into 10 to the -6 microcoulomb z square, and dl will be replaced by dz because the wire is placed in the z-axis and the limits are ranging from -2 to 2. So solving this constant comes out. Integration of z square is z cubed by 3 going from -2 to 2. So we get 12 into 10 to the -6 upon 3 into 8 plus 8, 16. So it becomes 64 microcoulomb. The total charge on this wire is 64 microcoulomb. So if the charge density was given, I was able to calculate the total charge on the wire. And similarly, we can have another question with charge density. The volume charge density is given. Rho v is 10z, and this much rho v is contained in a cylindrical volume, and the volume of the cylinder is defined by rho less than equal to 2. Now this rho can be sometimes referred to as r, the radius of the cylinder. So the radius of the cylinder is 2, and the cylinder is placed between -2 to +2. So half part of the cylinder is lying above the xy plane, half part of the cylinder lies below the xy plane. So that gives me the placement of the cylinder to be something like this. And of course we know that rho v is 10z. If we were to calculate dv is substituted as rho or r sometimes, d phi, d rho, dz. This is radius, this is z-axis, and this is the angle that the point makes with the x-axis. So this ranges from 0 to 360 degrees to span the entire cylinder. So the angle is 0 to 360, radius, and z is the length of the cylinder. Of course, when you do this, you need to take care of this. For cylindrical volumes or surfaces, we need to use this extra rho or r, whatever is specified as radius. Then we need to carefully put the limits, and it becomes a simple case of triple integration, where I can put the limits of z from -2 to 2, rho from 0 to 2, and 5 from 0 to 2 pi, and 10 comes out. And because this is simple multiplication inside without and all the independent variables. So I can say z square by 2 and phi will get a phi, and this will get rho square by 2, r square by 2, z square by 2. Now over here there's this school of thought that I want you to think upon, that when we put the values of phi from 0 to 2 pi, we'll get a finite value. When we put the value of rho from 0 to 2, we'll get a finite value. But when we get the value of z square by 2, when we put the value of z square by 2 from -2 to 2, here in this case this term will get is 0 here. So the entire thing will become 0. Now why does that happen? If you know the reason behind it, let me know in the comment section, because I've seen questions where the cylinder is placed above the surface of xy plane and we get a non-zero value. For example, if we place the cylinder from 0 to 4, then we would have gotten a non-zero value here. But that's not the point here. I wish to know from anybody who's watching this video that why does it happen, and if you know, please let me know in the comment section. But otherwise these questions are pretty easy to solve. If you're given the volume charge density, you can simply put that thing into the formula rho v dv, and simple mathematics will do the trick. And I hope this tutorial was of help. If you liked the video, give it a thumbs up, share this video among your friends, support the channel, and I'll see you in the next video. Take care, have a good day, good life ahead. Bye bye.